In this video, I'm going to discuss about linear programming. Before we discuss about linear programming, let's get to know about constraints. A constraint is a limitation or restriction. What is another term we can use for constraint? It is a limiting factor. We discussed about limiting factor analysis. Another term is bottleneck, and another term is a boundary. When it comes to linear programming analysis, instead of using limiting factor, bottleneck or boundary, we use the technical term constraint. Constraints are used to represent real-world restrictions and requirements that must be taken into account when making decisions. Constraints can be related to factors such as resource availability, production capacity, demand, time, budget, and other operational limitations. Under linear programming, we are going to discuss about two types of constraints. The first one is resource constraints. The company may have limitations on the availability of raw materials, labor, or machine capacity. These are known as the resources to the company. These constraints ensure that the total resources used by the production plant do not exceed the available quantities because the business can only use up to the available amount. So the production plan will not exceed the available quantities. The second type of constraint, demand constraints. The company needs to meet certain customer demands or sales targets. The production plan must satisfy the demand requirements within a given time frame. Simply, this is the demand for a product from the market. The business has to satisfy this demand. Now let's discuss about the main topic, which is linear programming. When there is only one limiting factor or constraint, limiting factor analysis can be used to make decisions on how to allocate scarce resources to the products. We already discussed about the limiting factor analysis, where we calculated the contribution per limiting factor for every product and we allocated the scarce resources from the highest contribution per limiting factor product to the lowest contribution per limiting factor product. So what will happen when there are more than one limiting factor? When there are more than one limiting factor or constraint, linear programming have to be used in order to make decisions on the optimum resource allocation. Because we can only use the limiting factor analysis when there is only one limiting factor. If there are more than one constraint or limiting factor, we cannot use the limiting factor analysis to make decisions. We have to use the linear programming when there are more than one limiting factor or constraint. When there are only couple of constraints, linear programming can be done manually. But when the number of constraints increase, a computer program has to be used because of the increased complexity. Simply this means when there are only couple of constraints, we can conduct the linear programming analysis manually by drawing a graph. But when the number of constraints increase, the complexity of the linear programming analysis will also increase. So then we have to use a computer program in order to find the optimum resource allocation or the optimum production plan. In this video lesson, we are only going to discuss about the manual method. These are the steps to follow when it comes to linear programming analysis. The first step, identify the variables. Simply this means we have to assign products to the x and y axis of the graph we are going to draw. For an example, let product A be in the x-axis. This means x-axis from now on represents the product A. Let product B in the y-axis. This means from now on y-axis will represent the product B. You can use the other way around as well. This means let product A be in the y-axis. Let product B in the x-axis. Remember that whatever option you select, you have to maintain this relationship throughout the following steps as well. The second step, model the objective function. Usually objective function denotes by letter set. We can use any other letter as well, but generally letter set denotes the objective function. The objective of the business is to maximize the profit. So letter Z is equal to the total contribution of the products. We have to model this objective function using the data given in the example. The third step, model the constraint functions. We have to identify the constraints for the given example and we have to model the constraint functions. The fourth step, draw the linear programming graph. How we can draw the linear programming graph? Each constraint has its own line in the graph. Simply this means if there are two constraints, there will be two lines. If there are four constraints, there will be four lines. If there are 100 constraints, there will be 100 lines. In order to draw the line for each resource constraint, 2 points should be identified using the constraint functions. Remember that we only have to identify 2 points when the constraint is a resource constraint. If the constraint is a demand constraint, there will be no need to identify 2 points to draw the lines. Demand constraint lines can be drawn directly without identifying 2 points. When we do an example, you will understand these points. And finally, the fifth step, find the optimum solution. Identify the feasible points within the feasible area. One of these feasible points will be the optimum solution that will maximize the profit. We will discuss about these terms when we do an example. An ISO contribution line or profit line will be used to identify the optimal feasible point. You are not required to draw this line and this line will be provided in the question. This is really important. You do not have to know how to draw this line. Using this line, you can find the optimal feasible point. How you can find the optimal feasible point? By using the contribution line or the profit line. The optimal feasible point is the last point that the ISO contribution line will touch when the line slide up parallelly. Simply this means when we draw the linear programming graph, the ISO contribution line will be provided like this. What you have to do is you have to slide this line upward parallelly until it touches the last feasible point. The last feasible point that the ISO contribution line touches will be the optimal feasible point. Then what we have to do is solve the simultaneous equations which have the optimal feasible point. X and Y values from this calculation will be the optimal production plan for each product. Now let's do an example so you can understand these steps clearly. Company K manufactures and sells two products which are product A and product B. Contributions of each product are $3 and $5 respectively. So they have given us this table which includes the raw material and labor hours that will be used to produce 1 unit of product A and product B. There are only 200 kilograms of material T and 240 labor hours are available in the company. Demand for both products are unlimited. Simply this means this company does not have a demand constraint because the demand for both products are unlimited. So there will be no demand constraint for this company. But they have two constraints which are resource constraints, material and labor. Draw the linear programming graph and find the optimum solution that will maximize the profit for the company. Now let's go back and see what are the steps. The first step, identify the variables. Simply this means we have to assign the products to the x and y axis. And another important thing to remember here that we can only use the linear programming when there are only two products. We cannot use the linear programming for one product or more than two products because there are only two axes, x and y. Let's assign product A and product B to the x and y axis. Step 1. Let product A be the x-axis. If you want, you can assign the product A to y-axis as well. But here I am going to assign product A to the x-axis and let product B assigned to the y-axis. The first step is done. The second step, model the objective function. The objective function denotes by letter Z, and this is equal to the total contribution of the products. So the second step, the objective function. So letter Z is equal to the total contribution. Here they have given us the contributions for product A and product B. For product A, contribution per unit is 3 multiplied by number of units of product A. We do not know the number of units of product A, but we know the x-axis represents the product A. So we put x here. Plus, for product B, the contribution per unit is 5 multiplied by y, because y-axis is representing the product B. So this is the objective function. X and y values are the number of units of each product. So this equation will give us the total contribution. The third step, model the constraint functions. Now we know there are two resource constraints, material T and labor hours. Now what we have to do is we have to model functions for each constraint. So the third step. So this is the function for material T. There are only 200 kilograms of material T, and each product uses 2 and 4 kilograms of material T in order to produce a single unit of each product. So unit of product A uses 2 kilograms of material T, and they are going to produce X number of product A's. Plus, product B is using 4 kilograms of material T in order to produce a single unit, and they are going to produce Y number of units of product B. Since material T is a constraint, which means they have a limited number of material T, which is 200 kilograms. So this is the maximum value they have, or this is equal to the usage of the production of product A and product B. So 200 greater than or equal to the usage of the material T in order to produce product A and product B. This is how we can construct the functions for each constraint. Now let's do this for labor hours. They have only 240 hours of labor, and product A uses 6 hours of labor, and they are going to produce X number of product A's. Plus, product B uses 3 hours of labor hour, and they are going to produce Y number of product B's. Since the labor hours is a constraint to the company, they only have 240 of labor hours. So this is greater than or equal to the usage of the labor hours in order to produce product A and product B. This is how we can construct the functions for each constraint. In this example, demand is not a constraint because they have a unlimited demand for both products. So there are only two constraints. Can you guess how many lines will be there in the linear programming graph? There will be only two lines because there are only two constraints. The number of lines in the linear programming graph is equal to the number of constraints the business has. This greater than or equal sign represents the right side of this function is always going to be less than or equal to the left side of the function because they only have 240 hours of labor. So they can only use the labor hours up to 240 hours. The fourth step, draw the linear programming graph. Each constraint has its own line in the graph. So there will be two lines in the graph that we are going to draw. In order to draw the lines for each resource constraint, 2 points should be identified using the constraint functions. We have two resource constraints. This means we have to identify 2 points for each constraint. And we do not have demand constraints, so we do not have to worry about this point. The fourth step. Let's identify 2 points for each constraint. Let's consider the material T first. This is the function we just modeled for material T. 2x plus 4y. Let's remove this greater than sign and let's keep the equal sign. So 200 is equal to 2x plus 4y. The first step is we are going to assign 0 to the x value. So what will happen? 200 is equal to 2 multiplied by 0 because we assign 0 to the x value here plus 4y. So this is equal to 0. So 200 is equal to 4y. Y is equal to 50. So when x is 0, y is 50. This is a 1 point. And now let's assign 0 to the y value. So what will happen? Same equation, 200 is equal to 2x plus 4 times 0 because we assign 0 to the y value. So this will become 0. 200 is equal to 2x. X is equal to 100. So when x is 100, y is 0. So these are the 2 points for the constraint of material T. And now let's identify 2 points for labor. This is the function for labor. Let's remove the greater than sign and let's keep the equal sign. We repeat the previous steps for material T again. So let's assign 0 to the x value. 246 multiplied by 0 plus 3y. So this will become 0. 240 is equal to 3y. Y is equal to 80. So when x is 0, y is 80. This is a 1 point. Now let's calculate the other point. 240 is equal to 6x plus 3y. Let's assign 0 to the y value. So 240 is equal to 6x plus 3 times 0. This is 0. 240 is equal to 6x. X is equal to 40. So when x is 40, y is 0. This is the second point. Now using these points, we can draw the lines for each constraint. Here is the graph. As I said earlier, this is the ISO contribution line or the profit line. This line will be provided in the question. You do not need to know how to draw this line. We assign product B to the y-axis and product A to the x-axis. So x-axis represents the product A and the y-axis represents the product B. So the first step, product A represents by the x-axis, product B represents by the y-axis. The second step is the objective function, which is z is equal to 3x plus 5y. This is the objective function. The third step is to model the constraint functions. So for material T, the constraint function is 200 greater than or equal to 2x plus 4y. For labor, the constraint function is 240 greater than or equal to 6x plus 3y. The fourth step is to identify 2 points for each constraint function. So for material T, the 2 points are when x is 0, y is 50, and the second point is when x is 100, y is 0. For labor, when x is 0, y is 80. The second point is when x is 40, y is 0. Now using these points, we can draw the lines for each constraint. Let's draw the line for material T first. The first point is when x is 0, y is 50. It is here. When x is 0, y is 50. The second point, when x is 100, y is 0. It is this point. Now we can draw the line using these 2 points. This is the line. This line represents the material T. Now let's draw the second line for labor hours. The first point is when x is 0, y is 80. It is here. The second point is when x is 40, y is 0. It is here. Now using these 2 points, we can draw the line. This represents the labor hours. So this is how we can draw the lines. As now you can see we have two constraints in the example. So there are only two lines in the graph. The ISO contribution line will be provided in the question. So you do not have to worry about this line. We are done with the first 4 steps. Now let's go back and see the fifth step. Find the optimum solution. Identify the feasible points within the feasible area. One of these feasible points will be the optimum solution that will maximize the profit. What is the feasible point and what is the feasible area? A feasible point refers to a combination of variable values that satisfies all the constraints of the problem. Variable values means x and y values. We can find the coordination for any point in the graph using x and y values. So a feasible point is any point that satisfies all the constraints of the problem. Because for every constraint we have a function. Let's go back. These are the functions for each constraint. So when we assign the x and y values of feasible points, these constraints will be satisfied. If we assign the x and y values of non-feasible points, these constraints will not be satisfied. A feasible point must meet the requirements and limitations specified by the problem's constraints while adhering to the non-negativity constraints. Simply a feasible point is any point which does not exceed any line from the left and from the bottom. This is how we can identify the feasible points using a graph. Let's read this point again. Simply a feasible point is any point which does not exceed any line from the left and from the bottom. From the left and from the bottom. This is the important part. Let's go back. This is the left side. When we enter into this graph from the left side, we can identify the feasible points. These are the points that will not exceed any line. When it comes to identify the feasible points, do not consider about the ISO contribution line. Only consider about the x and y axis and any other constraint lines. So we have here the y axis, x axis and the line for labor hours and the other line for raw material. Now let's enter into this graph from the left side. We are coming from this side and we have two feasible points, which is the origin because x and y axes are intercepting here. This is a feasible point. And up here there is another feasible point because the y-axis and the line for raw material intercepting here. So we enter into this graph. From the left side we can identify two feasible points. Is this a feasible point? Because here y-axis is intercepting with the labor hours line. This is not a feasible point because feasible points do not exceed any line. This point exceeds this line because this point is located next to this line. So this is not a feasible point. This is a feasible point and this is a feasible point. Now let's move further into the graph from the left side. Here is another point because labor hours and the raw material line is intercepting here. This is a feasible point. And let's move to the graph further from the left side and we can identify a point here. And let's move further. Here is another point. Is this a feasible point? This is not a feasible point because this point exceeds this line. Remember, feasible points do not exceed any line. So this is not a feasible point. Now we have four feasible points, which is the origin and here, here and here. Now let's go back to the point. As you can see, simply a feasible point is any point which does not exceed any line from the left. From the left means when we enter into the graph from the left side and from the bottom. This means when we enter into the graph from the bottom. Let's enter into the graph from the bottom and see we can identify any other feasible points. Here is the bottom and we enter into the graph from the bottom. We have 2 points, which is the origin because y-axis and x-axis is intercepting here. So this is a feasible point. We already identified this feasible point. And there is another feasible point because the labor hours line and x-axis is intercepting here. This is a feasible point. Is this a feasible point? This is not a feasible point because this point exceeds this line. Let's move up. There is a point because labor hours line and the raw material line is intercepting here. Is this a feasible point? Yes, it is because this point does not exceed any line. Feasible points can exceed the x and y axis. It is normal because this point exceeds this line. It is okay because x and y axis are already there. Feasible points cannot exceed any other line other than x and y axis. Let's move up. Here is another point. Is this a feasible point? Yes, it is because this point does not exceed any line other than the x and y axis. And let's move up further. There is another point. Is this a feasible point? This is not a feasible point because this point exceeds this line. So again we identified the same points as earlier. So there are four feasible points. Remember to check whether there are feasible points from both left side and from the bottom. Now let's assign letters for the feasible points we have identified. This is A, this is B, this is C, this is D. You can use any letter in any order. So in this example, there are four feasible points. Now let's go back to the fifth step. There is another new term, feasible area. What is a feasible area? Feasible region or feasible area. The feasible region is the set of all feasible points that satisfy the constraints of the problem. It represents the region or space in which the values of the variables can vary while still satisfying all the constraints. Simply, this is the area on the linear programming graph which is enclosed by the feasible points. Any point within or on the feasible region border will satisfy all the constraint functions. This is the important point when it comes to identify the feasible region. This is the area on the linear programming graph which is enclosed by the feasible points. Now let's go back to the graph and identify the feasible area. We identified four feasible points A, B, C, D. The feasible area or the feasible region is enclosed by the feasible points. This means this is the feasible region for this example. Because this area is enclosed by the feasible points we have identified. Do not consider about the isocontribution line here. So the area which is enclosed by the feasible points of A, B, C, D is the feasible region for this example. Simply this means any point within this feasible region will satisfy all the constraints. These are the constraints we have. So x and y values for any point within the feasible region will satisfy all the constraints. Feasible points can lie on the feasible border as well. These are also feasible points as long as those points are within or on the border of the feasible region. Now let's go back to the final step. Now we know what is a feasible point and feasible area, so the optimum solution that will maximize the contribution for the company will be within the feasible region. We already know the ISO contribution line. Now using the ISO contribution line, we are going to find the optimum solution or the optimal feasible point. The optimal feasible point is the last point that the ISO contribution line will touch when the line slide up parallelly. This is the ISO contribution line. This will be provided in the example. So what we are going to do is we are going to slide this ISO contribution line upward until it touches the final feasible point. And let's draw parallel lines to this ISO contribution line. And the feasible point D will be touched first. This is not the optimum solution. We are going to find out the final feasible point that will touch by the ISO contribution line. Secondly, the feasible point P, and finally the feasible point C. This is the final feasible point that the ISO contribution line touches when the ISO contribution line slide upward parallelly. So this is the point at which the contribution will be maximized. So how can we find the x and y values for the optimal feasible point? Let's go back and see. Solve the simultaneous equations which have the optimal feasible point. X and y values for this calculation will be the optimal production plan for the each product. Simply this means the optimal feasible point lies on the labor hours line and the raw material line. So we have to solve the simultaneous equations of labor hours and raw material, which are these two equations. After solving these simultaneous equations, we can get the x and y values for the optimal feasible point. 200. Let's remove the greater than sign and keep the equal sign. 2x plus 4y. 240 is equal to 6x plus 3y. This is the first equation. This is the second equation. If you know how to use the scientific calculation, you can get the answers directly. If not, you have to do this manually. What I'm going to do is I'm going to multiply the first equation by 3. So this will be 600 is equal to 6x plus 12y. This is the third equation. I just multiplied the first equation by 3. Now I am going to deduct the second equation from the third equation. Third equation 600, second equation 240. Third equation minus the second equation. This will cancel each other out. 360 is equal to 9 times y. So y is equal to 40. Now let's assign the y value to the first equation. 200 is equal to 2 times x plus 4 times 40 because y is 40. 200 is equal to 2 times x plus 160. 200 minus 160 is equal to 40 is equal to 2x. X is equal to 20. So these are the x and y values for optimal feasible point, which is this point. So when x is 20, y is 40. Now we can assign these values to the objective function. So this is the objective function. Z is equal to 3x plus 5y. Now let's assign the x and y values. 3 multiplied by 20 plus 5 multiplied by 40. This is equal to 60 plus 200. And finally this is $260. This is the maximum contribution that the company can earn by selling product A and product B at the optimal production plan. This also means they are going to produce 20 units of product A, 40 units of product B. They are going to produce more of product B because product B has the highest contribution. So they are going to give the priority to the highest contribution product and then the lowest contribution product. Now let's do this example. This is the same example as earlier, but there is a difference, which is now the company has demand constraints. Demand for product A and product B are 60 units and 30 units respectively. If you can remember, in the early example, there were no demand constraints, but now the company has demand constraints. Draw the linear programming graph and find the optimum solution that will maximize the profit for the company. So what is the first step? First step is to assign the products to the x and y values. So let product A be in the x-axis and let product B be in the y-axis. Simply this means from now on letter x is going to represent the number of units of product A and y is going to represent the number of products of product B. The second step is to model the objective function. Objective function denotes by letter Z, so this is equal to the total contribution. Contribution of product A is $3 per unit and there are X number of product A plus 5 is the contribution per unit of product B. There are Y number of product B. This is the objective function. Step 3. Model the constraint functions. There are now 4 constraints: raw material, labor, demand for product A and demand for product B. There is an important thing you need to remember here. Demand for each product is a separate constraint. Here we considered the raw material for both products as a one constraint, labor hours for both products as a one constraint, but we consider the demand for each product as separate constraints. So there are four constraints in this example: raw material, labor hours, demand for product A, demand for product B. So there will be four lines in the linear programming graph. Now let's model the constraint functions. For material T, the constraint function is the company has only 200 kilograms of material T. So this is greater than or equal to the usage of the material for in order to produce product A and product B. So 2x plus 4y. Now for labor. They only have 240 labor hours. 240 is greater than or equal to 6x plus 3y. Now demand for product A. The demand for product A is 60 units. So 60 is greater than or equal to x. This is because x represents the number of units of product A. The demand for product A is 60. This means the company has to produce only 60 units or less than 60 units. Now demand for product B, which is 30 units. So 30 is greater than or equal to Y. Y represents the number of units of product B. They only have to produce 30 or less than 30 units of product B. Now the fourth step. This is where we have to identify 2 points for each resource constraint. Let's go back to the fourth step. Here, as you can see, in order to draw the lines for each resource constraint, 2 points should be identified using the constraint functions. And if there are demand constraints, there will be no need to identify 2 points to draw the lines. Demand constraint lines can be drawn directly without identifying 2 points. This means we have to identify 2 points for each of these resource constraints, simply assigning 0 to the x and y values as we did earlier. These are demand constraints, So we do not have to identify 2 points for each demand constraint. When we draw the linear programming graph, we can directly draw these lines. So for material T, we identified the 2 points, which are these values. When x is 0, y is 50. When x is 100, y is 0. For labor, when x is 0, y is 80. When x is 40, y is 0. Now the final step, we have to draw the linear programming graph. Here y-axis represents the product B and x-axis represents the product A. Now let's draw the graph. First of all, let's draw the constraint line for material T. When x is 0, y is 50, which is this point. When x is 100, y is 0, which is this point. Now we can draw the line. This is the material T line. For labor, when x is 0, y is 80, which is this point. When x is 40, y is 0, which is this point. Now we can draw the line. This is the line for labor. How we can draw the lines for demand? The demand for product A is 60 and x-axis represents the product A values. So mark the 60 on the x-axis, which is this point, and just draw a vertical line like this. This is the demand constraint line for product A. The demand for product B is 30. Y-axis represents the number of units of product B. So mark the 30 on the y-axis, which is this point, and draw a horizontal line. This line represents the demand for product B. And finally, this is the ISO contribution line. This line will be provided in the question. Now we are done drawing the graph. Now we have to identify the feasible points. Let's enter into the graph from the left side. As you can see, there are two feasible points, which is this point and the origin. Is this a feasible point? This is not a feasible point because this point exceeds this line. Is this a feasible point? This is also not a feasible point because this point exceeds these two lines. So let's move further. There is a point. Is this a feasible point? Yes, it is. Because this point does not exceed any line. Is this a feasible point? This is not a feasible point because this point exceeds this line. And is this a feasible point? This is also not a feasible point because this point exceeds this line. And now let's move further. We can identify a point here. This is a feasible point. And let's move further. Is this a feasible point? This is not a feasible point. Is this a feasible point? This is also not a feasible point. And likewise, these 2 points are also not feasible points. Now let's move from the bottom. There are two feasible points, which is this point and this point. We already identified these 2 points. Let's move up and there are two feasible points here. Every other point is not a feasible point, like these 3 points. So we have four feasible points, which is this point, this point, and this point. Now we can mark the feasible region, which is enclosed by these feasible points. So this is the feasible region. Now what we have to do is we have to move the ISO contribution line upward parallelly until it touches the final feasible point. So let's move up. Now it touches this feasible point. This is not what we are looking for. We are looking for the final feasible point that the ISO contribution line touches. Let's move up further. Now it touches feasible point D, and finally it touches the feasible point C. So this is the optimum feasible point. Now what we have to do is we have to find the x and y values of this point. We do not consider about the feasible point A here because it is below the ISO contribution line. We only consider the final feasible point that the ISO contribution line will touch. So in order to find the x and y values of the optimal feasible point, we have to solve the simultaneous equations of these two lines, labor hours and demand for product B, because intercepting point of these two lines is the optimal feasible point. So the function for the labor hours is 240. Let's remove the greater than sign and keep the equal sign. 6x plus 3y. This is the first equation. And the second function is for demand for product B, which is 30. Let's remove the greater than sign. Keep the equal sign. This is equal to y. This calculation is simple because we already have the y value, which is 30. All we have to do is we have to assign the y value to the first equation. So let's do that. 240 is equal to 6x plus 3 multiplied by 30. 30 is the y value coming from the second equation. 240 is equal to 6x plus 90. 150 is equal to 6x. X is equal to 25. Now we have the values for the optimal feasible point. When x is 25, y is 30. This means the company is going to produce 50 units of product A and 30 units of product B. Now let's assign the x and y values to the objective function so that we can calculate the maximum contribution that the company is going to earn at the optimal feasible point. This is the objective function. Let's assign the x and y values. 3 multiplied by 25 plus 5 multiplied by 30. So the maximum contribution that the company is going to make is $225. And another important thing to note here, they are going to produce more profitable product because product B has the higher contribution, which is $5 per unit. And they are going to produce less profitable product because product A has only $3 per unit contribution. Now we are going to discuss about two very important terms under linear programming. The first one is slack resource. After the optimal solution is implemented, some constraints may have excess or extra amounts left. This is known as a slack resource. We just identified the optimum solution for this example, which is to produce 25 units of product A and 30 units of product B in order to maximize the contribution. After this solution is implemented, there can be resource constraints that have excess amount or extra amount left. These are known as the slack resources. We only consider the resource constraints to be slack or non-slack resources, not demand constraints. Simply this means we are not going to consider demand as a slack resource or non-slack resource. We are only going to consider about the resource constraints as slack resource or non-slack resource. If a constraint has a slack, it is also known as a non-binding constraint. You need to know about these terms. If a constraint does not have a slack, which is the opposite, it is known as a binding constraint or a scarce resource. The lines in the linear programming graph which have the optimal feasible point on are scarce resources. If a constraint does not have a slack, it is known as a binding constraint or a scarce resource. How can we identify the binding constraints or scarce resources? This is how. We have to first identify the optimum point, which is here. The lines on which the optimum point is on are the scarce resources. In this example, labor hours and demand for product B. But we do not consider about the demand to be a resource. So in this example, the only scarce resource is the labor hours. So every other resource constraint is a slack resource, which means after implementing the optimum solution, there will be excess amount of that resource. But after implementing the optimum solution, there will be no labor hours left because labor hours will be fully utilized, but an amount of raw material will be left. We do not consider demands to be resources. The other important term is shadow price. Shadow price is the highest acceptable premium that a business is willing to pay for an additional unit of a scarce resource. Simply, this means this is the highest acceptable premium that a business is willing to pay in order to obtain an additional unit of a scarce resource. So, in the early example, the scarce resource was the labor hours. So, if the company wants to obtain an additional unit of that scarce resource, which means 1 hour of labor hour because additional unit. Here the unit is hours, so the additional unit will be 1 hour of labor, the highest acceptable premium that the business is willing to pay is known as the shadow price. There is another definition for shadow price. Shadow price is the extra contribution that can be earned by having an extra unit of scarce resource. Simply, this means if the business can obtain one more labor hour, which is the extra unit of scarce resource, what is the extra contribution that the business is going to earn, which is also known as the shadow price. These two definitions are described in the same term, which is shadow price. So, when it comes to questions, you need to know about these two terms. Any value below the shadow price is acceptable because the shadow price is the premium that the business is willing to pay in order to obtain an additional unit of a scarce resource. So, any value below the shadow price is acceptable because it will lower the cost to the company. This is because select resources have an extra amount or an excess amount. It means this resource is not scarce. The resources which are binding constraints or scarce resources will only have the shadow price because availability of those resources will be limited. In order to obtain an extra unit, the company has to pay an premium amount. So, slack resources do not have shadow prices. Only the binding constraints or the scarce resources have shadow prices. Now let's do this example. This is the same example we discussed earlier. In this example, what we have to do is what are the scarce resources for the company? Calculate the shadow price of the scarce resource. If the company wants to obtain more of the scarce resource, what is the price of one unit of that scarce resource? So first of all, let's identify the scarce resources for the company. And this is the optimal feasible point. Using this graph, we can directly identify the slack resources and the scarce resources. Since this optimum feasible point lies on the labor hours and the demand for product B lines, these are the scarce resources. Since we do not consider the demand to be a resource, the only scarce resource in this example is labor hours. Because at the optimal feasible point, the labor hours will be fully utilized, which means there will be no excess amount after implementing the optimum solution. So labor hours is the scarce resource for the company. Calculate the shadow price of the scarce resource. So how we can calculate the shadow price? Let's go back to the definitions of shadow price. The second definition, shadow price is the extra contribution that can be earned by having an extra unit of scarce resource. So in this example, labor hours is the scarce resource. So we can simply calculate the shadow price by dividing the maximum contribution, which is 5. Here are the contribution values 3 and 5. Take the maximum contribution value and divide it by the usage of the scarce resource. Product B has the $5 of contribution. So we use the 3 hours here. This is equal to $1.67. This is the extra contribution that the company can earn if they can obtain one more extra unit of the scarce resource. Simply this means if they can obtain 1 hour of labor, they can earn an extra amount of 1.67 contribution. If the company wants to obtain more of the scarce resource, what is the price of 1 unit of that scarce resource? So always remember, shadow price is the premium. This means this is the extra amount that the business is willing to pay. Usually the company can buy labor hour for $2 per hour. So if the company wants to obtain more of labor hours, they have to pay 2 plus the shadow price amount 1.67, which means they have to pay $3.67 in order to obtain one extra unit of scarce resource. In this case, one labor hour. Always remember, shadow price is not the final price. Always remember, shadow price is not the final price. Shadow price is the premium or the extra amount that the business is willing to pay. Usually they have to pay $2 per labor hour. After implementing the optimum solution, if the company wants to obtain one more hour of labor, they are willing to pay 1.67 extra in order to obtain that labor hour. So the total price they are going to pay is 3.67. Any value below this 3.67 is acceptable because it will lower the cost to the company. 1.67 is the highest premium that the business is willing to pay. They are not willing to pay above this amount. Now let's do this example. A company has conducted a linear programming analysis for their two products and identified the optimal production plan which earns $1,200 of contribution. Simply this means if they assign the x and y values of the optimum production plan, maximum contribution that can be earned is $1,200. If they can obtain one additional kilogram of a scarce resource, which is $5 per kilogram, the new maximum contribution is $1,203. What this means is this is the contribution that the company is going to earn if they can obtain one additional unit of scarce resource. So the new contribution will be 1203 if they can obtain one additional kilogram of a scarce resource. Now let's go back to the definition. Shadow price is the extra contribution that can be earned by having an extra unit of scarce resource. So what is the extra contribution that the company can earn? It is the difference between these two contribution values, which is equal to 3. They are going to earn $3 of extra contribution if they can obtain one additional kilogram of a scarce resource. So this is the shadow price. So what is the final value that the business is going to pay if they want to obtain one additional kilogram of a scarce resource? So the total price of an additional kilogram of a scarce resource is equal to 5 plus 3, which is equal to $8. This is the final price they are going to pay. This is the usual price which is given here, and this is the premium value or the shadow price or the extra amount that the company is willing to pay in order to obtain an one additional kilogram. So the final price is $8. Now let's do this example. This is the first example we did in this video. For this example, there are no demand constraints. The maximum contribution that can be earned is $260. If the company wants to obtain more of labor, which is a binding constraint, what is the shadow price? So in this question, they are directly giving us that the labor hours is a binding constraint. This means there will be a shadow price for the labor. They have also given us the maximum total contribution that can be earned at the optimum feasible point. So, as now you know, this is the objective function which denotes by C is equal to 3x. Let's consider x to be the product A, 5y. Product A will be the x values, product B will be the y values. So in this example, they are directly giving us the total maximum contribution, which is 263x plus 5y. And we can also model the constraint functions. For raw material T, what is the constraint function? 200 greater than or equal to 2x plus 4y. For labor, 240 greater than or equal to 6x plus 3y. We can calculate the shadow price for a binding constraint. In this example, it is labor. Shadow price happens after the optimum solution is implemented. And now what we have to do is we have to calculate the shadow price. So all the equations here will be different for the shadow price. Now the company is going to obtain an additional unit of labor. So now let's construct the new functions. The maximum contribution that can be earned will be different now. So this is Z1 is equal to 3x1 plus 5y1. This is the first equation. Now let's construct the constraint functions. For raw material, it is going to be the same, but the x and y values are going to be different. x1 and y1. This is the second equation. We are going to obtain one more unit of labor hour. So this will become 241. Pay close attention. We only had 240 hours of labor. But here we are going to obtain one more unit of labor, which means 241. This is greater than or equal to 6x1 plus 3y1. This is the third equation. Now what we have to do is we have to solve these two simultaneous equations in order to find the x1 and y1. Let's find the x and y values manually. I am going to multiply the second equation by 3. So 600 is equal to 6x1 plus 12y1. This is the fourth equation. Now I am going to deduct the third equation from the fourth equation. These two will cancel each other out. Y1 is equal to 39.89. Now using this y value, let's find out the x1 value. So what I am going to do is I am going to assign the y1 value to the second equation. X1 is equal to 20.22. So these are the new x and y values when the business obtain one more unit of labor. Now let's assign these x1 and y1 values to the first equation so that we can find the new total contribution. Z1 is equal to 3x1 plus 5y1. So the new total contribution is $260.11. As now you can see, after obtaining 1 hour of labor, the contribution has increased from 260 to 260.11. So now let's calculate the contribution difference, which is equal to 260.11 minus 260. This is equal to 0.11. This is the extra contribution that the company can earn if they obtain one additional labor hour. So this is the shadow price of 1 labor hour, 0.11. This is the highest premium amount that the business is willing to pay in order to obtain one additional labor hour. So what is the total price of one additional labor hour? It is equal to 2 plus 0.11. This is equal to 2.11. This is the total price that the company has to pay in order to obtain one additional labor hour, because the usual labor rate is $2 per hour. Now they have to pay a premium of 0.11. Now let's discuss about the limitations of linear programming. There can be only two products. As now you know, we can only use two products when it comes to linear programming analysis, because there are only two axes. When there are more than two products, we cannot use the linear programming analysis. This is a limitation. Products are infinitely divisible, and those parts can be produced and sold. This means products should not be a whole number. Let's say 3 units, 4 units, or 5 units. There can be also decimal values. Let's say 3.1 units, 4.8 units. These values are also acceptable. Because there is an assumption under linear programming, we can produce these amounts of products and these can be sold as well. In reality, this is a limitation because we cannot produce or sell fractional amounts of units. It has to be a whole number of units. Linearity assumption. Linear programming assumes that the relationships between variables and constraints are linear. This means that the objective function and constraints must be expressed as linear equations or inequalities. Real world problems often involve nonlinear relationships, and linear programming may not accurately capture those complexities. Single objective optimization. Linear programming focuses on optimizing a single objective function. In many real world situations, there are multiple conflicting objectives that need to be considered simultaneously. Linear programming does not easily handle problems with multiple objectives, and trade offs between them may not be adequately captured. Integer and discrete variables. Linear programming is well suited for continuous variables, but it becomes challenging when dealing with integer or discrete variables. Problems that require integer solutions, such as allocating a fixed number of resources or selecting whole number of units, fall under the realm of integer programming or mixed integer programming. These problems are generally more complex and computationally intensive. Computational complexity. The computational complexity of linear programming can grow rapidly as the number of decision variables and constraints increases. Solving large-scale linear programming problems with a high number of variables and constraints can be computationally intensive and time-consuming, requiring advanced algorithms and powerful computational resources. Uncertainty and dynamic situations. Linear programming assumes that the problem parameters are known with certainty and remain constant over time. However, real-world problems often involve uncertainty and dynamic conditions where parameters can change. Linear programming models may not be flexible enough to handle such uncertainties and dynamic decision making. Modeling limitations. Building an accurate linear programming model requires a clear understanding of the problem and its constraints. However, in some cases, it can be challenging to represent real world problems accurately and capture all relevant factors in a linear programming model. Oversimplification or incorrect assumptions in the model can lead to suboptimal or unrealistic solutions. Thank you for watching. See you in the next video.